Let's finish up lecture notes 4. We're going to talk about the sampling distribution of the OLS estimators. So just like y bar has a sampling distribution, the OLS parameters have sampling distributions. Because the OLS estimators are computed from randomly drawn samples of the population, different samples yield different estimates of beta hat 1 and beta hat 0. So just like the sample average depends on the sample that's drawn, the regression line, the estimated beta 0, beta hat 1, those depend on the sample that's drawn. And this is the source of sampling uncertainty in beta hat 1. Therefore, the estimators themselves are random variables with probability distributions. And so we're, in this lecture, going to define what those probability distributions are. So our goal is to quantify the sampling uncertainty associated with beta hat 1. What do we mean by the sampling uncertainty? Well, we're going to be doing t-stats and confidence intervals and p-values around beta hat 1. We use beta hat 1 to test hypotheses such as beta 1 equals 0, or we can set it to whatever we want it to, but the most often is we're going to set it to, our null hypothesis is going to be that the slope is equal to 0, or there's no relationship between two variables. We can construct confidence intervals for beta hat 1, but all of these require figuring out the sampling distribution for beta hat 1. So the sampling distribution for beta hat 0 and beta hat 1. First, recall the OLS assumptions. The expected value of u conditional on x is equal to 0. This one was also implying expected value of u equals 0. Data are collected by random sampling, so xi and yi are IID, and x and y have finite fourth moments, or we called this in the previous lecture, outliers are rare. If these assumptions hold, then the expected value of beta hat 1 is equal to beta 1, and OLS is unbiased. Yay. So remember, the definition of unbiasedness is the expected value of the estimator. So expected value of y hat, in the case of the mean, is equal to mu y. In this case, it's the expected value of the slope or the expected value of the intercept are equal to their population values. In large samples, we can invoke the central limit theorem to show that beta hat I are normally distributed. So when I say I, I'm indexing the betas, so that's going to be beta hat 0 and beta hat 1. In reality, the central limit theorem says that the joint bivariate distribution of beta 0 and beta 1 is normal, but this implies that the marginal distributions are also normal. So in large samples, the distribution of beta hat 1 is, this little symbol here is distributed. So beta hat 1 is normally distributed with mean beta 1, the population parameter. Remember, expected value of beta hat 1 is equal to beta 1, and variance sigma squared beta hat 1. So this thing is going to be unknown, but we will estimate it. And the distribution of beta hat 0 is normal with mean beta 0, the population value of it, and variance sigma squared beta hat 0. The exact finite sampling distribution of beta hat 1 has the following properties. The variance of beta hat 1 is written as, so this is sigma squared beta hat 1. This thing is equal to 1 over n, where the numerator is the variance of xi minus its mean. So mu x is expected value of xi, population mean times the ui, and what are these? These are the errors in the regression equation. So if we wrote out, these are the population errors, by the way, not the sample errors. So if we wrote out the population regression function, we would get that. And that's what we're multiplying x minus its mean, or the average difference between x and its mean, by the population errors, and that's over the variance of x squared. So this shows that beta hat 1 is more precisely estimated, or the variance of beta hat 1 is smaller when the variance of x is larger. So as the variance of x, the denominator, goes up, this variance of beta hat 1 goes down. And it's also smaller when the variance of u, the error terms, is small. And that's sort of intuitive, right? So what we're really saying is if we have x and y and we have some data, and the data looks like this, and we fit a regression line to it, so that's a pretty obvious relationship there, right? Fit a regression line to it, looks something like that. The variance of x is basically how far x is, how much spread there is in x. And in this case, I've drawn it so there's a lot of spread in x, and so we're going to be more precisely estimating the slope, the rise over the run of this line, if the variance of x is large, if we have a lot of data points, and also if the UIs are small, right? So the UIs are the difference between each data point and the line, right? We know those are the UIs, right? The difference between the data points and the line. If they're small, we're going to be more confident in the estimated regression line compared to if they're large. Let's draw the alternative here. So the alternative would be, let's suppose the variance of x is really small. So we have a bunch of data points, but they're all collected right around there. How do we draw a line through that? What is the best fit line? Ordinarily squares is probably going to give us something like that. It's just going to be beta hat 1 equal to 0. There's no relationship because it can't figure it out because the variance of x is really large. The other thing is if the u's are larger, then we're going to be less precisely estimating this too. So we can draw this on the first graph. So if we add more data points around here, it's less clear that that's the best fit, that this line here is the best fit to that data now. Property 2. Beta hat 1 converges in probability to beta 1, or in other words, it's a consistent estimator. As n goes to infinity, as the number of observations that we draw increases, this thing converges in probability to its population value. So basically, if we got all of the, if we drew the entire sample, as n goes all the way up to the entire sample, we're getting closer and closer to the true population value. Property 3, when n is large, beta hat 1 has the following distribution. So remember, how do we normalize or how do we standardize a normal random variable? So if beta hat 1 has a normal distribution, to standardize, we subtract mean, step 1, and divide by standard deviation. That's how we standardize a normal random variable. So we know that beta hat 1 is a normal random variable by the central limit theorem, and so then we can subtract off the mean, the expected value of beta hat 1. In this case, it's going to most often be the hypothesized value of beta hat 1, and we divide by the standard deviation, or the variance of beta hat, the square root of the variance of beta hat 1. And when we do that, we're left with a standard normal random variable. Let's summarize a couple of things about lecture notes 4. So one of the main things that I want to get across is we have a population regression model and a sample regression model. The population regression model is written without hats. It's what we have here, right? The sample regression model is going to be what I have below, and again I made a little error here. So if we have the predicted wage hat with the predicted beta 0 and beta 1, we shouldn't have the error term. So let me erase that error term. So this error should not be here, right? Because the values over here, wage hat, are the values that fall along the regression line. I just want to make that clear. So these, if this is wage and this is education, wage hat falls on that regression line. The other way to write this is wage, to observed values of wage, plus the error term. So I'm writing the error term as E, it could be U. So we have to put that error hats. And those would be getting us back to the data points. So like wage there, and then we're adding on the error term to get us back from the line. This bit's the line. Get us back from the line to the data points. We need that error term. A few more things that are going to help you on the problem set. So EI or UI is the error term. It's a random variable. It's an unknown random part of the model. Because the Y value is random, the errors between the Y value and the population regression line will also be random. Education is the observed explanatory variable. In most cases, this is considered predetermined with respect to the dependent variable, wage in this case. So this is not a random variable in a lot of cases. This is a constant. Beta 0 and beta 1 are population parameters. They are real but unknown numbers that we are trying to estimate, so they are constants. They don't depend on the sample that we've drawn. Right, so these are not random variables. They're constants. Wage are the dependent variables. The sum of a constant beta 0 and education and which is predetermined, and then a random component, the error term. So it is considered a random variable. EI, the residuals, is the estimate of the error term, and so therefore it's random as well. And the beta hat 0 and beta hat 1 are parameter estimates which depend on the current sample. And we've already defined, this whole lecture was about defining their distribution. And so if we're talking about something that has a distribution that's non-trivial, then it has to be a random variable. Okay, so that finishes up lecture notes 4. And that's about it.